Today, we're diving into the really elegant math behind a problem that's, well, everywhere. How do complex systems figure out what's real when they're just getting a constant stream of messy, unreliable data?
Okay, so picture this, a self-driving car. Its GPS might be off by a few feet, the cameras can get tricked by shadows, and the sensors on its wheels, they aren't perfect either. So it's getting this constant flood of slightly wrong information. How in the world does it take all those imperfect clues and build one single confident idea of where it actually is? That's the heart of the problem we're going to tackle.
You know, this whole field has a name, state estimation. And it's not just for cars. We're talking rockets, robots, even trying to predict the economy. It's really the art of finding the truth, what we call the state, by cleverly mixing all these noisy clues with what you already know about how things are supposed to work.
Now, the real world is messy, right? So to really get a grip on this, we're going to start in a kind of perfect, simplified world. It's called a linear-Gaussian system. Now, linear just means everything is nice and predictable, straight lines, basically. And Gaussian means all the errors, all the noise follows that perfect bell curve shape you've probably seen. And there's a really good reason we start here.
This quote just nails it. We start with these linear systems because we can actually solve them exactly. No guesswork, no close enough. We can find the one perfect answer, and that gives us this incredibly solid foundation to build on. So here's the game plan. We're going to take two totally different approaches, two completely different ways of thinking to solve this one problem. And the big question is, are they going to lead us to the same place?
All right, let's start our journey down these two roads and meet our two competing philosophies.
So on one side, you've got the Bayesian way of thinking, the belief approach. It's all about probabilities. It starts with this kind of vague cloud of possibilities for the car's entire trip. Then, every new piece of data we get helps to sharpen that cloud, to bring it into focus. And on the other side, we've got the map approach. This one is pure optimization. It doesn't care about clouds of belief. It just wants to find the one single best path that perfectly explains everything we saw. Okay, let's take our first path. We're going down the road of Bayesian belief. So the way this works is pretty cool. We start by defining something called a prior. It's basically a giant mathematical description, this big Gaussian distribution of every possible path the car could have taken, based just on physics. Then, and this is the key part, we take all of our measurements, from the beginning to the end, and we use them all at once to update that initial belief. What we get is a new, much sharper belief, and we call that the posterior.
And after all that, what do we actually get? We get a nice, clean equation for the mean, the statistical average of that final sharpened up cloud of possibilities. It's like finding the center of gravity for our final belief. Just hang on to that word, mean. All right, time to switch gears. Let's check out our second road, the path of map optimization, and see how it gets to the answer.
This approach is, well, it's a lot more direct. First, we create something called a cost function. Think of it like a penalty score. Any path you can imagine gets a high score if it breaks the laws of physics or doesn't match our sensor readings. But a path that explains everything perfectly, that gets a super low score. Then, it's simple. We just use math to find the one single path that has the absolute lowest cost. And here's where it gets really interesting. When you do the math to find that minimum cost path, what do you end up with? A system of linear equations that you need to solve. That sounds kind of familiar, doesn't it? It feels like our two very different roads might be leading to the same place after all. So, after traveling down two completely separate paths with two totally different philosophies, where did we end up? Let's take a look. Both roads lead us right here to this one single beautiful equation. Now, don't worry about what all the letters mean right now. Just know that the z on the right is basically all our noisy measurements, and the x on the left is the true path we're trying to find. Both ways of thinking, the belief way and the optimization way, they both arrive at this exact same place. This is it. This is the answer. But wait a second. What gives? How is that even possible? One method was looking for the average of a whole cloud of possibilities. The other was hunting for the single best path. How on earth can they give us the exact same result? And this is the magic trick, right here. In the clean, perfect world of a Gaussian bell curve, the average value, the mean, is in the exact same spot as the most likely value, the peak or the mode.
So the Bayesian approach was looking for the mean, the map approach was looking for the peak, and because we're in this perfect little bubble, they found the exact same point. Pretty cool, right? So we have this one elegant equation. Fantastic. But there's a practical problem. For a long trip, this equation could have millions of variables. I mean, how could you possibly solve that? Well, it turns out our equation has a hidden superpower.
When you actually write out the big matrix from our equation, that H transpose W inverse H thing, it looks like this. It has this really beautiful, simple structure. It's mostly empty space, see? The little stars are the only places with numbers. The rest is all just zeros. And that happens for a simple reason. The car's position right now only really depends on where it was just a moment ago. This amazing property is called sparsity. Now, if this matrix were totally full of numbers, solving it would be a computational nightmare. It would have a cost of O of k cubed. What that really means is if you make your trip twice as long, it takes 8 times longer to solve. It just blows up and becomes impossible really, really fast. But thanks to that beautiful sparse structure, we can solve it in O of k time. That's linear. So if you double the trip length, it just takes double the time to solve. That incredible efficiency is what makes this whole thing actually work in the real world. Sparsity is the secret sauce.
All right, let's wrap this all up. What are the big things to take away from this whole journey?
Okay, first, state estimation is how we find what's real from a bunch of imperfect clues. Second, in the perfect linear Gaussian world, two completely different philosophies, belief and optimization, they magically end up at the exact same answer. Third, that answer is one single elegant equation. And finally, and maybe most importantly, there's a hidden sparse structure in that math that makes it astonishingly fast to solve. So we have this perfect answer that works perfectly in a simple world. But that just leaves us with a huge, tantalizing question, doesn't it? What happens when we have to leave this clean little world behind? What happens when things aren't nice straight lines and the noise isn't a perfect bell curve? What happens when the real world gets messy?